And it's my great pleasure to introduce our third speaker for today, Chao Li, who will speak to us about Beilinson-Bloch conjecture and the arithmetic inner product formula.
Thank you very much, Sid. Thanks for the introduction. And I would like to thank all the organizers for the great opportunity to speak to celebrate Steve's birthday. I think I first met Steve relatively recently in 2014 in Paris. I was a graduate student attending a summer school and followed by a conference on the GGP conjectures. And Steve gave introductory lectures on his program on the arithmetic theta function and the arithmetic zero wave formula. And as a graduate student, I was immediately struck by his lectures, not only because the beautiful mathematics there and also his very lucid and passionate lecture style. I'm very glad to say that all these things I learned in the very first lecture I learned from Steve is going to play a role in today's talk. I hope I'm going to mention that. And I think it's fair to say that these two papers, which are posted on arXiv, would not have existed if not for Steve's original insights. And I'd like to thank him for that and thank him for the great impact on the younger generation like me. So I'm going to report on recent joint work with Ethan Liu on Beilinson-Bloch conjecture. So let me begin by motivate this conjecture slowly with this more familiar BSD conjecture. All right, so let me start with a rational elliptic curve defined by cubic equation. And there are two most important invariants related to this elliptic curve. One is algebraic rank, defined to be the rank of its model vehicle with a group of rational points. The other one is defined analytically, it's called analytic rank, defined to be the order vanishing of its L function at central point s equal to 1, which I denote by Rn. So the celebrated conjecture of Birch and Swinner-Dyer back in the 60s says that these two invariants, although seemingly defined in a completely different way, are actually equal to each other. These two integers are equal. And furthermore, they predicted a precise formula for the leading coefficient of the L function at central point in terms of various interesting arithmetic invariants of elliptic curve. So I'm not going to go through all of them in detail, but just mention there are two global invariants appearing in this formula. One is the regulator, which is determinant of the R by R matrix formed by the Néron-Tate height pairing of rational points generating the Mordell-Weil group, the free part of the Mordell-Weil group. Right, here's the Néron-Tate height pairing. It's a non-degenerate symmetric bilinear form on the group of rational points valued in real numbers. Right, and the other one, the global quantity appearing as a mysterious Tate-Schiff-Roerich group. All right, so this conjecture is quite remarkable because links two worlds of different nature, one algebraic nature, the other analytic nature. And it's also quite remarkable by quoting from Tate. Right, so this remarkable conjecture relates the behavioral function L at a point where it's not presently known to be defined. Right, at the time when Tate wrote that article, we don't know the full modularity theorem for elliptic curve except the CM cases. So the left-hand side don't know it's defined, the order vanishing at central point, to a group shot that is not known to be finite. Right? So the right-hand side also doesn't make sense. So this is really a conjecture equality between two things that are not defined. Of course, later we know that the modularity theorem makes sense on the left-hand side, and in many cases, we actually can prove the finding of this Shah, so this equality actually makes sense. All right, so the BSD conjecture, of course, is supported by a huge amount of numerical evidence, but theoretically, we don't know too much. It's still widely open in general, but as everybody knows, much progress has been made in the rank 0, rank 1 case. All right, here's the theorem of Grozaki and Kolivaki, proved in the 80s, says that if the analytic rank of E is either 0 or 1, then the algebraic rank is also 0, 1, as predicted by the BSD conjecture. And moreover, in these cases, we know how to prove this finding of Shah, and in many cases, the precise formula for the leading coefficient are also known. Right, so how do they prove this remarkable equality between the two ranks? Well, the proof actually can be thought of as combining two inequalities. One is a consequence of the Grozaki formula, which says that if the analytic rank of E is 1, then algebraic rank is at least 1. Namely, under this analytic assumption, we're able to construct a non-trivial rational points of infinite order. All right, so the other inequality is supplied by Kolyvagin theory of Euler system, which has the following implication, namely the analytic rank is either 0 or 1, and the algebraic rank is bounded above by the analytic rank. And you can easily see, combining these two inequalities, we'll get these two equalities in these cases. All right, so today I'm going to focus on the first implication, but just suffice to say that both steps actually crucially relies on zero-Wegener points on modular curves. These will be generalized to more general special cycles on Shimura varieties. All right, any questions so far? That's good. All right, so the Beilinson-Bloch conjecture will be a vast generalization, conjecture generalization from elliptic curves of the rationals to arbitrary smooth projective variety over a number field. Okay, so let me take X to be such a variety over number field K. All right, so one natural generalization of the model V group is applied by the Chao group of algebraic cycles of codimension M on X. All right, then the most arithmetically interesting part of this Chao group consists of cycles that are geometrically cohomologically trivial. Right, so you don't have non-trivial information from geometry. All right, so for this particular subgroup of cycles, Beilinson-Bloch also constructed an analog of height pairing, now called Beilinson-Bloch height pairing, on a group of cohomological trivial cycles of codimension M and arithmetic complementary dimension. Again, this is a Beilinson pairing valued in real numbers. All right, so this naturally takes care of the algebraic side. So on the analytic side, the relevant L function will be the motivic L function associated to this particular motive. All right, so concretely will be attached to a compatible family of L-adic Gauss representations come from the degree 2m minus 1 cohomology of this variety, X. All right, so the conjecture of Beilinson-Bloch formulated in the 80s says that, again, there will be equality between ranks. One is analytic rank, namely the order vanishing of this motivic L function at the central point at S equal to M, and an algebraic rank, which is the rank of this relevant Chao group of codimension M cycles. Okay, and then further make a precise conjecture for the leading coefficient, so up to some non-zero factors. This leading coefficient will be equal to, again, the regulator, now with respect to the Beilinson-Bloch height. All right, so in the simplest case, if you take your smooth projective variety to be just the elliptic curve of the rationals, and M equals to 1, namely looking at the dividers on the curve, right? So the Chao group of dividers on curve of degree 0 is nothing but the model V group of E. Right? The L function of motive H1 of E is nothing but the Euro-Hasse-V L function of E. And the Beilinson-Bloch height in this case is closely related to the Néron-Tate height pairing. It's just up to a sign. All right, so you can see the Beilinson-Bloch will recover BSD as a special case. All right, any question about the Beilinson-Bloch conjecture?
Sorry, what is Zi, Zj here?
What is?
The Zi and the Zj prime in number 2?
That's just the basis of the free part of Chao group. Yeah.
Okay, thanks.
Similar in the case of the ellipticals. Thanks for the question. Any other questions? All right, so again, this is quite a remarkable conjecture relating to two worlds of different nature, but it's also quite remarkable by the criterion of Tate. So I have to warn you that in general, both sides of this inequality are unconditionally defined. They're not really defined at the moment. All right, on the analytic side, this motive L function in this generality is not known to have analytic continuation to the central point S equal to M. Okay, and when codimension M is bigger than 1, this Chao group is also not known to be finitely generated. Right, so we don't know the right-hand side is a finite integer. All right, but I guess history has told us that you shouldn't be too afraid. And in fact, the mathematicians are very brave to actually still make progress or attack this conjecture. And in fact, the original idea of Langlands was, his program is trying to address the first bullet point, right? To isolate a class of varieties where you can at least access the central point of the L function, right? And these classes of variety are isolated by Langlands, namely the class of Shimura varieties. All right, so the aim is to express these motivic L functions of certain Shimura varieties associated to G, the classical group G, as a product of automorphic L functions, where these L functions has more accessible analytic properties. So I'm going to put our in situation that is the most interesting. So I'm going to put 2n minus 1, this index is exactly in the middle dimension. Right? So in particular, my variety will be odd dimension. And I'm going to assume my automorphic representation is kind of most primitive ones, and assume it's tempered cuspidal. Right? So in good situations, these analytic properties of the L function can often be established. So that makes sense of the left-hand side of the Beilinson-Bloch conjecture. So in its generality, of course, this Chao group is not known to be finally generated, but at least we can test if it's non-trivial or not. Okay, so I'm going to propose an unconditional prediction of the Beilinson-Bloch conjecture in the same spirit as the Grozagi formula, as I mentioned on the previous slide. All right, so now I can formulate the Beilinson-Bloch conjecture. Now it's complete unconditional for Shimura varieties, namely if the automorphic L function has analytic rank 1, then the algebraic rank of a certain pi isotypic component of the Chao group is non-trivial, right? The rank is at least 1. All right, so I have to address now, this conjecture actually makes sense, right? It doesn't depend on any other conjectures. All right, any questions so far? All right, great. So what is known about this conjecture? It's formulated unconditional. All right, not many cases. Actually, I can list all of them on this slide. Of course, the original case of modular curves, as in the work of Grozagi, and laid vast generalization to the case of Shimura curves by Shou Zhang, Kuda Rapport Yang, Yuan Zhangzhen, and Yifeng Liu in various complete generality. And these are curve cases, and recently there's exciting breakthroughs. Hang Xue, who proved the first case where you can deal with varieties of higher dimension. You consider Shimura threefold is attached to the unitary group U11 cross U21. All right, so this is in the context of the arithmetic GGP, under the additional global assumption that pi is endoscopic. All right, so this assumption, in fact, allows Hang Xue to reduce in an interesting way to the case of unitary Shimura curves that it was considered by Yifeng Liu. All right, so naturally you wonder maybe what about the higher dimensional situation? And is this just a wishful thinking, or is some truth to this conjecture? All right, so the main theorem I'm going to discuss today, an impressionist version of the main theorem, is that this conjecture holds for class of unitary Shimura varieties of arbitrary high dimension, so U to n minus 1, 1, under the additional local assumptions on the automorphic representation pi. Okay, so that's the general shape of the theorem. So of course, I'm going to tell you precisely what these Shimura varieties are and what these local assumptions are precisely. And already, not surprisingly, in the course of the proof, we're going to prove certain analog, high dimensional analog of the Grozagi formula. All right, any questions?
Yeah, Chao, are there difficulties in even defining the pi isotypic component of the Chao group?
I don't think so. You can always define it, but the properties of it is not clear.
But I mean, you don't know that the action of the Hecke algebra factors through the action of the Hecke algebra on the middle cohomology, right?
It's on the Chao group, so you can view it as a representation as a adelic group. Then just take the finite part of this pi, take it as a typical component. Yeah.
I'm just worried it could be 0 or something. I mean,
or simply, or if more concretely, you can just view this Chao group as a Hecke module and just localize at the ideal associated to the maximum ideal of pi. That's something more concrete, but less a bit of weaker.
I guess I'm bothered by the fact that pi occurs in cohomology, but I don't know that it occurs on the Chao group, do I?
But the Hecke algebra acts
on the Chao group. That I agree. Yeah. Okay.
Right. Thanks for the question. Any other questions?
Hi, Chao. May I ask a quick question?
Yes.
You need pi why do you need? Is it essential that you assume pi cuspidal? I mean, probably for your result, but do you not expect this for?
Well, that's the most interesting case, I would say.
Yeah,
Yeah, you can consider more general, but
make the same conjecture.
Yeah, but presumably they will be reduced to the case of more primitive case.
Okay.
Yeah, but if you look at middle cohomology, the pure motives, they are expected to be cuspidal. But you can look at the degree from the middle, then it would be less cuspidal, I guess.
Okay,
all right, any other questions? All right, of course, Steve wouldn't be surprised by such a theorem. So let me remind you this famous paper that already made an appearance several times in this conference. And in his paper of Steve, he actually wrote, our results suggest it might be possible to establish Kurosawa type formulas exactly for Shimura varieties of this type. All right, so I guess this theorem can be read as Steve is absolutely right. All right, and of course, Steve is also absolutely right when he wrote this.
What is the phrase after that in certain other sporadic cases?
For example, the triple product case. Right. Okay, so Steve was also absolutely right when he wrote that many serious problems actually block the way in the higher dimensional case. And I guess my goal is to give you some idea of the recent advances, ingredients that goes into the proof of this theorem. All right. Any other questions before now I describe a more precise version of the theorem? If not, now let me tell you what these relevant Shimura varieties are. All right, so I'm going to fix a CM extension of a totally real number field. All right, so one way to describe these unitary Shimura varieties is to fix a totally definite incoherent adelic Hermitian space of rank M. All right, so here this incoherent adjective means that this adelic Hermitian space is not the base change of a global Hermitian space, or equivalently by the Hasse principle that the product of a Hasse invariance of these local Hermitian spaces is -1 instead of +1. Right? So this language is useful when you pick an arbitrary infinite place of the totally real field. It will give rise a nearby coherent space that are actually global. Right? So what you do is you keep all the local Hermitian space to the same, but you change the signature from definite to n-1 at a particular infinite place. All right, so the relevant group will be the adelic group of this adelic Hermitian space, and I'm going to fix the level subgroup in the adelic points of this adelic group, which is of course also the adelic finite adelic points of the honest unitary group. All right, so my unitary Shimura variety will have dimension n-1 over the reflex field E, such that if you pick an infinite place of your choice, then this corresponding complex points of the Shimura variety, we have this complex uniformization, right? So where D is the Euro Hermitian symmetric domain in this case. For unitary group signature n-1 is just a complex ball of dimension n-1. All right, so these are all familiar, but I have to warn you a little bit. This is not the Euro unitary Shimura variety associated to unitary similitude group that has more appearance in global long length correspondence. Right, so in fact, this is associated to an honest unitary group, and this is Shimura variety of abelian type. Right, so it causes difficulty because it doesn't have the Euro modular interpretation in terms of abelian varieties of additional structures. Right, so fortunately, even in this abelian type case, its tau cohomology and L function are computed in the forthcoming work of Kissen-Shin and Yihang Zhu under the help of endoscopic classification for unitary groups. So at least long length, the original program can be realized for these cars of unitary Shimura varieties. All right, so that's about the Shimura varieties. Now let me tell you what are these automorphic representations. So these will live on the quasi-split unitary group. So let me fix an even dimensional standard skew Hermitian space, W, and UW will be a quasi-split unitary group of even rank n equals to 2m. And my pi will be cuspidal automorphic representations associated with the adelic points of this quasi-split unitary group. All right, so now I'm going to make a series of technical assumptions about the field extension and about this ramification of this holomorphic representations. The first assumption is certain ramification assumption on this CM extension. So I'm going to assume that E over F is split at all two adic places. And for simplicity, I'm going to assume F is not Q, right? So in particular, my Shimura variety will be compact automatically. So I don't need to worry about the technical complication coming from compactification. All right, so I'm going to assume that all the ramified places of F that, all the places of, finite places of F that is ramified E are always unramified over Q. That's really some technical assumption. And I'm also assume E is Gauss over Q or contains an imaginary quadratic field. That's not necessary, but just for the purpose of talk, let me assume that for simplicity. All right, so now I'm going to assume at Archimedean places, the pi v is a holomorphic discrete series with this particular Harris changer parameter. So that's a familiar, so kind of simplest kind of a Harris changer parameter that the direct generalization of wave 2 holomorphic modular forms. All right. So for finite places, I'm going to assume certain local ramification assumption. So all the pi v will be tempered, and if v is ramified, then I'm going to assume pi v is spherical with respect to the stabilizer of this lattice of integer points. And if v is inert in the CM extension, I'm going to assume it's unramified. All right, no ramification, always a little bit of ramification, so almost unramified representation. And moreover, if pi v is almost unramified, I'm going to assume v is unramified over the rationals as well. All right, so I guess an easy way to remember this assumption is that I pose some sort of minimum kinds of ramification at ramified and inert places, but I impose no conditions at split places. All right, but now let me briefly remind you what this almost unramified representations are. All right, so this means that this pi v on the quasi-split unitary group has a non-zero Iwa Hori fixed vector, and its Satake parameter contains the pair Q and Q inverse, and the rest of the Satake parameters are complex numbers of norm 1. Right, so you can think of this as kind of Steinberg representation on a 2x2 block. Right, so in particular, if you take m equals to 1 and n equals to 2, U2, this is really just a Steinberg representation on the quasi-split unit U2. All right, so an alternative equivalent way of describing this, you look at the theta left from the quasi-split unitary group to the non-quasi-split unitary group of the same rank, and it is spherical with respect to the stabilizer and the almost self-dual lattice. All right, so this is where this terminology almost unramified comes from. All right, any question about assumptions? All right, so now one advantage of stating these local assumptions, I can pin down the root number of these representations pi very easily. So let me consider a set of finite places where v is inert and pi v is almost unramified. Then under my previous assumptions, the global root number for the complete standard L function, standard base change L function of this pi equals to this precise formula. So it has some contribution -1 from these almost unramified places and certain Archimedean contribution. Right, so this is a consequence of the local theta epsilon dichotomy for theta correspondence for unitary groups. All right, so in particular, in a case we are interested in when the analytic rank is 1, so the global root number is -1, that gives us some parity constraint on this set S pi. In particular, I can canonically associate a totally definite incoherent space of rank n such that I exactly prescribe the local sign to be -1 for those places in this finite set S pi. All right, so in particular, I can run my previous general construction and arrive at a unitary Shimura variety, exactly putting in my favorite situation of dimension 2n-1, all right, or the reflex field E. All right, so I'm going to look at the symbol will denote the localization of this Chao group at the maximal ideal of the Heck algebra away from the bad primes, which acts on this Shimura variety. All right, so now my precise version of this main theorem is that if pi satisfies all the previous assumptions, then the implication of the analytic rank is 1 implies this sort of pi localized Chao group is non-trivial holds, as long as when the level subgroup is sufficiently small. All right, any questions about this statement? Okay, I guess the first question is this theorem empty? All right, so I have a list of assumptions. Well, how serious are these assumptions? But as I said, you only impose some sort of ramification, like sort of unramified or almost unramified, which looks like a square-free conductor assumptions at inert and ramified places. But at the split place, I have no assumptions. So you can easily cook up to examples of this sort. So let me give you a very concrete example coming from very explicit motives, coming from symmetric power of elliptic curves. All right, so let me remind you, this is our theorem. All right, so now let me cook up an example of this kind of L function appearing in the theorem. All right, so let me take a modular elliptic curve over this totally real field F with a complex modification, such that the 2m-1 symmetric power of this elliptic curve is modular. Now you can actually construct many examples of this sort by recent advances on the symmetric power factorial lift. All right, so I can also assume a ramification assumption. Remember, I can put all the ramification as split places, and I can make this theorem applicable. So I can make an elliptic curve that has boundary reduction that only occurs at places that are splitting. All right, so now there are many examples. In fact, I just picked the example appeared in Dick's talk related to the frequent McVee's curve. Well, this is an elliptic curve of this totally real cubic field that has only boundary reduction at 2. And 2 is split in this Seaman extension, so that is satisfied. All right, in fact, you can cook up many other examples of this sort. All right, so if I assume my field satisfies previous assumption, then always this is such automorphic representation pi satisfy my previous assumption, so that the symmetric power L function of H1 of this elliptic curve base change to E is in fact agree with this automorphic L function. All right, and in fact, in this case, you actually arrange that the ramification only appears at split places, so this finite set S pi is just empty. So the global root number is simply governed by the parity of M and the parity of the degree of the field extension. So in particular, the theorem will apply when pi, when this product is odd. Right? For example, we can take F to be totally real cubic field and M is 3. All right, so the theorem will tell you that if the analytic rank is 1 for this symmetric power L function, then there's a piece of the Chao group of the Shimura varieties not true.
Implicitly, you are requiring M to be odd here. So
M to be odd. M is odd and F is odd degree.
Yeah, so that's
but
you're missing half of the your result, right?
That's right. That's right. Because I assume this put this ramification assumption. So of course you can generally allow ramification at other places. Any other questions? All right. So at least this theorem can have a lot of interesting applications. Examples that are coming from arithmetic elliptic curves. All right, so now my next goal is to explain a little bit of the proof and what the ingredients. Right, so if you look at this implication, right, so the left-hand side and right-hand side are very far from each other. And one side is purely analytic, and I have to use this analytic equation to get some consequence on the Chao group. And how does this link happen? Of course, these non-trivial cycles are constructed by the method of arithmetic theta lifting. It was really the original idea of Steve Kudla and later developed in this particular unitary case by Ethan Liu in his series. All right, so tell you what these arithmetic theta lifting are, and I'm going to run a baby example of Hagener points. All right, so let me remind you the classical Grotz-Zage formula. So let's look at the modular curve of level n. Let's classify pairs of elliptic curves together with a cyclic n isogeny between them. As a construction of the Hagener divisor, which can be described in terms of modular interpretation, namely look at the pair of elliptic curves with extra endomorphism. by ring of integer of a certain imaginary quadratic fields, satisfying so-called Hagen hypothesis. Right, so you get a divisor, which is element of the Chao 1 of the modular curve. So by the theory of complex multiplication, they are defining over a very small number field. Right, so now if you have an elliptic curve or conductor n, together with using the modular parameterization, you can use these Hagen divisors to get a k-rational point, a Hagen point on this elliptic curve. All right, so the Gross-Arge formula roughly says that up to simple non-zero factors, the first derivative of the base change L function e to k at the central point is equal to the narrow-Tate height of these Hagen points. All right, so if you choose this auxiliary imaginary quadratic field suitably, then one can get the implication as I mentioned in the previous slide. But one thing you already see, right? So there's this little subtlety that you have to make this particular choice of auxiliary imaginary quadratic field. So next I'm going to tell you a way to remove this sort of arbitrary choice of k, namely using the generating series of Hagen points. All right, so let me take this notation PD to be the trace of this Hagen points from the imaginary quadratic field of discriminant negative d down to Q. All right, so now I get rational points in the elliptic curve, in the Q points of the elliptic curve, but I have to warn you that it may depend on the choice of D, even when in the simplest situation when the rational points is just a free group of rank 1. Right, here's a simplest example, the first elliptic curve, or rank 1 over Q, conductor 37. Right, so in this case, EQ is just a one copy of Z, and generated by this obvious rational point 0, 0. Right, and this corresponds to a weight 2 modular form of level 37, which you can, here's an explicit Q expansion, and you can use this modular form to compute the Hagen points. All right, so here are the list of Hagen points with the first few small discriminants. And you can see, right, when you vary the discriminant D of the imaginary quadratic fields, you get different points. And sometimes the points can be actually not so obvious on the curve, right? For this 6 minus 15 is not obvious on this curve at all. All right, so one way to encode these different arithmetic complexity is, well, I have this generator. I can just write all these points as a common multiple of the generator, right? And I get a sequence of integers indexed by the discriminant D. What are these integers, right? -1, -1, 1, -6, etc. Well, the miracle is that this CD appears exactly as a Fourier coefficient of another modular form, now in this case of weight 3/2. Okay, so these coefficients exactly match with this integral multiple. And what is this weight 3/2 modular form? Well, not so surprisingly, it's actually maps to the weight 2 modular form under the theta, under the Shimura correspondence, which of course is also an instance of the theta correspondence. All right, so what you learn from this example is that you can make a generating series of Hagen points, and you recognize the coefficients of these multiple is in fact the modular form of weight 3/2. So you can view this generating series as a modular form valued in the Mordell-Weil group of E rather than in the complex numbers. All right, and this is not only happened for this particular curve, but in fact, you can define the generating series on arbitrary modular curve of level n, right? And from this generating series of Hagen points, it's always a modular form of weight 3/2 valued in the Chao group, Chao 1 of the modular curve. And in Steve's terminology, that's the simplest instance of the arithmetic theta series, where you replace the real representation numbers of definite quadratic forms to this indefinite case, right, SO2-1 case by these Hagen points. All right, but now the advantage is now I can use this arithmetic version of the theta series to make a lifting, right? By pairing this theta lift with the weight 3/2 modular forms corresponding to the weight 2 modular forms of the elliptic curve. All right, so I'm going to arrive at a F isotypic component of the Chao group. In this case, can be identified with the rational points of the curve itself. All right, so now the advantage is you don't need to make any particular choice of the D okay, you just consider all of them. All right, so now this arithmetic theta lifting doesn't depend on any particular choice and complete canonical. And from Steve's point of view, now I can reformulate the theorem of Gross-Kohlin and Zagier formula in terms of just the arithmetic theta lift is standard on theta height is equal to the derivative of the elliptic curve now over the rationals. Right? We don't need to do any base change. All right, so now this is the link I'm going to present. So I'm going to generalize these arithmetic theta series to unitary Shimura varieties and use them to make the arithmetic theta lift. All right, so these theta series will be constructed by special cycles, which now has appeared several times in this conference as well. All right, but so far, any questions about this picture? All right, if not, let me now review the special cycles. These are coming from construction of Shimura subvarieties. So let me pick a vector in the Hermitian space that are positively definite. All right, so I can look at this orthogonal complement, which is another Hermitian space, but now has one rank lower of the same type. All right, so now I have a Shimura subvariety associated to this orthogonal complement that will define a Shimura subvariety of a codimension 1 in this the original Shimura variety X. And in fact, you can not necessarily take a rational vector, but arbitrary adelic vector with a global totally positive norm. Then there will exist a rational vector and an element in the adelic unitary group such that I can translate, given arrive at this X by a G translate. Then can define a special divisor simply by doing a little translate by this group element G to get a special divisor on the unitary Shimura variety X. All right, then you can now do multiple times, take a sequence of vectors in the finite adelic points of the Hermitian space. Let's assume that the moment matrix given by the inner products of these entries is a global Hermitian matrix that is positively definite, then can define a special cycle now of codimension M, right, by simply forming a fiber product over X. All right, so that's special cycles. There's a supply of special cycles of arbitrary codimension. Now I'm going to make it more like a theta series appearing in a zero wave formula by encoding an additional Schwarz function and doing the average. Right. So let's take an arbitrary Schwarz function that is k finite, k invariant. Then I'm going to define a weighted special cycle by just averaging these special cycles z of x with a given moment matrix, and I weight them by the values of the Schwarz function. All right, now what you arrive is an element in the Chao group of codimension M on X. All right, so this is well defined when the matrix is positive definite. Okay, but with a little bit of extra care, you can actually extend this construction to get elements in Chao group for arbitrary semi-definite elements. All right, so now you can form that's generating a series of special cycles. Now it looks like the Q expansion of a certain holomorphic modular forms now on a quasi-split unitary group. Right? That's in fact exactly the conjecture. It's very natural for me like in the 90s that the formal generating series actually converges absolutely and defines a modular form on the quasi-split unitary group. Right? But now not valued in C, but valued in the complexification of the Chao group. All right, any questions so far about the conjecture? Okay, so a lot of progress has been made towards this conjecture. And of course, the origin of this conjecture is that its modularity was known if you map these cycles to Betty cohomology. Right? It's already known by the work of Kuda and Milson. And this conjecture is also known for the divisors case, and for more general M, Yifan Liu proved that the modularity actually follows from the absolute convergence of the series. Okay, so this reduced the conjecture to absolute convergence of the series. This is still not known, but I have to mention and remind you that the analysis conjecture for orthogonal Shimura varieties of the rationals is actually known. Right? So such a desired absolute convergence was proved by Bruni and Rob a few years back. All right, so in this generality for the unitary case, the conjecture is still open in general, but recently Zhao Xia has proved this conjecture for certain imaginary quadratic fields of relatively small discriminant. Okay, so I guess it's not too optimistic to say that this conjecture may be eventually within reach if you combine methods of recent methods with some extra new ideas. All right, but anyway, for the talk of today, I'm going to assume this modularity conjecture holds in the unitary case. All right, so now I can mimic the construction in the elliptic curve case. All right, so I'm going to take a holomorphic modular form in pi and define the arithmetic theta series by simply pairing this Culas generating series against this holomorphic form. All right, so I'm going to arrive at certain cycles, presumably lying in the pi isotypic component of the Chao group. All right, so this is big theta will be denote arithmetic theta lifting. All right, so now I can tell you the precise formula that generalizes the Grozagi formula. All right, so let me assume pi still satisfying the previous assumption. Assume the root number is -1 and the Culas modularity conjecture holds. And for any holomorphic form in pi and any test function, curly phi up to simpler factors depending on these choices, I have equality between the central derivative of pi with the Beilinson-Bloch height of these arithmetic theta lifting. Okay, so that's the key formula that makes a link between the analytic quantities and the arithmetic geometric quantities. All right, any questions so far about the statement?
Yeah, Chao, sorry, I have a question.
Mm-hmm.
Do you have to modify the cycle somehow to make them homologically trivial?
That's right. So you have to apply certain Heck operators to make the cycle homologically trivial. And this is understood in that sense, right? Because the pairing is somehow Heck equivariant. That's a great question. Any other questions?
So when your original theorem, you don't assume Coulomb modularity, how do you get away with that?
Yes, I'm going to mention that. That would be a little trick using proof by contradiction. Okay, I'm going to mention that at the end when I describe the proof. Any other questions?
Well, this cohomology is automatically trivial, right? For when you take this theta lifting. So
Under my assumptions, yes.
right. So you actually you don't need to apply anything, right? I mean,
Well, the way you prove this cohomological trivial is by using the Heck operators to make it to show that it's cohomological trivial, and using the Heck equivariance. That's something you need to show, but it's true.
Okay.
And Chao, presumably
Yes.
part of this claim is that this arithmetic theta lift actually lies in the pi component of the Chao group. Is that something formal, or does that actually require
No, this actually relies on very crucial these assumptions when we produce Heck operators to show that.
I see.
It's not
So that's
formal.
something to
It's
prove.
not formal. Yeah.
Okay.
Great. Any other questions? All right. So maybe to convince you that this is really explicit formula, I want to make this formula a little bit more precise in a simpler situation. All right. So let me assume that pi is actually unramified or almost unramified at all places, all finite places. Right. So there's no ramification, higher ramification at all. Then there's a notion of holomorphic new form in this case. Let me take such a holomorphic form. And then let me take the test function to be the most interesting one, the characteristic function of self-dual or almost self-dual lattice at all finite places. All right, so now I can really make all these simpler factors explicit. All right, so this is the derivative of the L function, a certain Boolean L function, that's the L function of the gross motive, unitary group. A certain Archimedean zeta integral, you can compute explicitly some factors of 2, pi and gamma factors. And a certain local zeta integral coming from the bad places, you can compute explicitly as a rational function of Q, right? And it's equal to a certain sine times the Beilinson-Bloch height. All right, so you can make it extremely explicit in the simplest case. And of course, whenever you prove such a explicit formula, you would do a reality check, right? Because both sides have certain positivity properties. So the derivative of the L function by the Riemann hypothesis of always non-negative. Right? That's a consequence of the Riemann hypothesis. And the right-hand side, the Beilinson-Bloch is also has certain positivity as property. And in fact, Beilinson's Hodge index conjecture predicts that the sign is precisely this -1 to the m. Right? If you think about the divisor case, m equals to 1, this is really -1 of Beilinson-Bloch height. That's the narrow plate height, which is always non-negative. All right, so our formula, of course, doesn't show either Riemann hypothesis or Beilinson's index conjecture, but at least shows that these two conjectures, very big conjectures, are compatible with our formula. All right, that's a nice thing to have. All right, any questions? All right, so in the remaining 15 minutes, I'm going to tell you a bit about some details of the proof. All right, so but maybe before that, a summary of, I draw a complete analogy starting from the BSD conjecture, which generalized to higher dimensional to the Beilinson-Bloch conjecture, replacing the modular curves by unitary Shimura varieties, Hagen points by special cycles. Then I form the generating series of special cycles and make an arithmetic theta lifting. Right? And the natural generalization of the Grotz-Zage formula is the arithmetic inner product formula relating the derivative and Beilinson-Bloch height of the arithmetic theta lifting. Right? Of course, this terminology, arithmetic inner product formula, comes from really the Rallis inner product formula, right, where you have the classical situation relating the central value of the L function with Peterson inner product of Euro theta lift. Okay. This can be sort of an arithmetic analog of that. All right, so of course the starting point will be the way to access the L function is using the doubling method of Piatexi, Shapiro, and Rallis, developed in the unitary case by Yamana. Right, so I can have an integral representation of the standard L function of pi in terms of an integral, right? It's pairing of, on the doubling group, doubling two copies of UW of phi tensor 5r, paired against the certain Siegel-Eisenstein series. Now on a unitary group of twice the size. All right, so on the arithmetic geometric side, I can also unwind the definition of the arithmetic theta lift to get a formal expression like so. So the Beilinson-Bloch height of the arithmetic theta lift can be also written as an integral. Again, with this phi tensor 5r, now with another arithmetic kernel function, right, given by the Beilinson-Bloch height of the special generatings of the special cycles. All right, so if you want to compare these two quantities, the analytic quantity and the arithmetic geometric quantity, it suffices to compare these kernel functions, right? The Eisenstein series and these Beilinson-Bloch height of a generating series. All right, so to prove this derivative is equal to the Beilinson-Bloch height, it suffices to compare the derivative of the Eisenstein series at the central point s equal to 0 with Beilinson-Bloch height of these generating series. Of course, the right-hand side can be thought of as a arithmetic analog of theta series, and this can be viewed as this terminology, arithmetic Siegel waveform. All right, so how to prove such a thing? Well, the Beilinson-Bloch height, by definition, is a sum of local indices. Right, so it has a local decomposition on the favorable situation that this local contribution indexed by all the finite and infinite places, right? And each local indices are defined in terms of L-adic homology at finite places. If you look at the non-singular Fourier coefficients, T coefficients of the Eisenstein series, it has a factorization into local terms, again indexed by the places. So if you take the derivative, it will Leibniz rule turns the derivative, turns the product into a sum, right? Again indexed by the places. So it is suffice to compare the local terms one by one, right? Place by place. That's the key comparison. And we would like to prove, at least for the singular, non-singular terms, that is certain identity between the local terms of the analytic side at V with the local indices appearing in the Beilinson-Bloch index. Height pairing, all right. All right, so how to prove such a, that's really the meat, right? This is really the key identity relating analytic information and arithmetic geometric information. So in the previous work, when m equals to 1, it turns out that both sides can be computed explicitly, right? So these are two numbers. It's highly non-trivial to compute these numbers, but it turns out miraculously there are relationships. After computing both sides, they are actually miraculously matched with each other. Okay, but explicit computation are infeasible. They take an arbitrary m, higher dimensional. All right, so needless to say, we're not going to do explicit calculation in generality for general m. All right, so now let me tell you what the main ingredients for doing such a computation at both finite and infinite places. All right, so the computation at the finite places, and in fact, that's the source, the technical complication is the source of all these assumptions, the ramification assumptions I told you, is to first link this local indices appearing in the Beilinson-Bloch height, which is a priori defined using L-adic homology. It's very abstract and very hard to compute, to something more concrete. Right? So to arithmetic intersection numbers on such regular integral models of unitary Shimura varieties of PEL type. That's considered by, in the work of Kuda-Rappaport, and more recently by Rappaport, Smithling, and Zhang. Right? So at least these arithmetic intersection numbers living on these integral models are something more concrete that can help, you can hope to compute. And second is you're going to relate these arithmetic intersection numbers, some more concrete objects, now to these analytic quantities. All right, and the first one is, right, you really study these L-adic. First of all, you have to make integral extensions of these special cycles to these particular regular integral models, right? And then we're going to relate these priorly L-adically defined local indices to intersection numbers. And that's not easy. Right?
What do you mean L-adic?
I mean, these Beilinson indices, local indices, are defined in terms of winding numbers in L-adic homology of the generic fiber. It's not defined in terms of intersection.
Okay.
Yeah. In fact, it only use generic fibers, so so in general, you can have, you don't even know they are regular models. Right? It's only defined on the generic fiber. All right, so to make this connection, we use really sophisticated use of heck operators, and along in a way that you get really the correct interpretation of these Beilinson-Bloch height in terms of arithmetic intersection number. We have to prove certain vanishing of localized L-adic homology of these integral models. Right? But even the existence of these regular integral models requires impose a particular ramification assumption on the level of these Shimura varieties. That's where the source of these Shimura varieties, and even proving these.
So when you say L-adic, means that the values L-adic number?
These values are L-adic numbers, a priori, yes.
So you use L-adic Theta cycles inside.
So you're right that primarily these numbers define our L-adic numbers, right? But if you interpret it in terms of arithmetic intersection numbers, you know these are actually rational numbers, eventually. All right. All right. So these are, to proving these statements, make the connection in the first part actually already requires all these assumptions to kick in. And second part is also requiring all these assumptions. So this relation between the arithmetic intersection numbers on integral models and the derivative Beilinson series is actually the content of a conjecture made by Kuda-Rappaport, as was recently proved by Wei Zhang and myself. All right, so the argument is not an explicit computation, but instead induction argument using uncertainty principle, which is a sort of tool from local harmonic analysis. All right, and This is originally formulated for inert places. And if you want to get a result like I stated, also allow certain ramification for the ramified places, we need a certain extension of the original conjecture to ramified places. And that's proved in our paper for certain integral model called the exotic smooth integral models. Right, so the level structure also tells you where these assumptions at ramified places come from. All right, so this is what happens at finite places. That's a rough idea. So the main input is this proof of Kuda-Rapoport conjecture and the relation between arithmetic intersection number and the local indices defined by Beilinson. All right, so on the Archimedean places, and we use crucially the Archimedean arithmetic Ziegler wave formula proved by Ethan Liu in the unitary case, and later independently using a different method by Garcia and Sankaran, in actually much more generality. All right, so you use the Archimedean arithmetic Ziegler wave formula, which is a relation of this sort, but not quite when you know, in this business, when you actually prove something related to arithmetic geometry, you have to make some sort of holomorphic projections to make the identity. All right, but for us, we can use a little bit trick because we only care about the formula after you do arithmetic theta lifting, meaning only after pairing with holomorphic forms. Right, so we can manage to avoid use of holomorphic projections. Right. In any case, now we have enough identities to actually produce the precise identity we needed for the proof of arithmetic inner product formula, at least at non-singular terms. All right, so to finish, now we need how to deal with the singular terms. And kill the singular terms on both sides. We prove the existence of certain special Schwartz functions with regular support at two split places. At the same time, ensuring that the local zeta integrals for these special Schwartz functions are non-vanishing. Okay, so this idea of making use of test functions of regular support, of course, I think already appeared in the work of Yuanzhang Zhang. Okay, you need to prove the existence of such test functions. All right, so if you have regular support at two split places, the analytic side actually has 0 singular terms. Right, so the comparison will be finished for the special phi for non-singular terms. Right. Now for this general case, if you the case you really care about, like the characteristic function of a self-dual lattice, you will really like a singular phi doesn't have regular support. Right. For that, we use a little bit representation theory. So you use the multiplicity 1 result for doubling method, which can be proved in the template case, as in our case. All right, so now you deduce, using this non-vanishing local zeta integrals, you can deduce that this identity is actually true for arbitrary phi. All right, so this is so far now all uses Kudela's modularity. But if you only want the non-vanishing of the corresponding Chao group, you can run the same computation, but now without Kudela's modularity to get a little bit less precise information, simply by a proof contradiction. By contradiction, right? So if I assume there's all the relevant cycles are already 0 in the Chao group, so in some sense, I'm making a theta lift where the generating series is just 0. Of course, 0 is always modular. There's no convergence issue at all. So you can formally do this computation, assuming it's 0. But on the other hand, my analytic computation, right, the analytic assumption is the derivative is non-vanishing. I get a contradiction by assuming that there's no cycles, no non-trivial cycles at all. All right, so you get a bit of weaker implication, but now it's unconditional on the modularity. All right, so I hope I give you some ideas of the main ingredients in the proof. I guess it's appropriate to end my talk with theta series and quadratic forms, as Steve is a fan of that. So it's a little puzzle for sum of squares. So here's a question for everybody. So when is the sum of first n squares again a square? The answer is on my last slide. And happy birthday, Steve.
Okay, thank you very much, Chao, for that wonderful talk. Okay, while we're all working at the puzzle, are there any questions, comments?
I have a question about this vanishing, about the localization. I mean, is this by like in this work of Zhu and Tian and so on, that you impose, so to speak, something p-adic on the Hacker eigenvalues?
No, that's different. No. So this vanishing result is a careful study of the singularities of the special fiber. So for example, you can take the almost unramified situation where the integral model is semi-stable. Then you can understand the cohomology using a Rapoph-Zink spectral sequence. You use that.
Okay.
Yeah, so you understand the special fiber and their stratification and compute the cohomology. And it's more difficult in the split case because we don't impose any ramification restrictions. We actually have to work with integral models with arbitrary high dreamfield level structure. Then you have to understand the singularity of the special fiber of these particular integral models, which appeared in Michael Harris' work with Taylor. And you have to use geometry of these refined Newton strata Igusa towers.
So here you need a vanishing of a sort of rational coefficient. I mean QL coefficient.
Correct.
I think in the 5 author paper, maybe Michael was referring to, we were trying to prove some vanishing of moduli or sort of torsion.
Torsion coefficient. Yeah. It's different.
No, I was not thinking of 5 authors.
Oh, I see. Sorry, misunderstood your reference.
No, I think Zhu and Chao, I think. Too many Chinese here, I think. Anyway, this sounds different.
It's different, yeah.
Okay, are there any other questions or comments for Chao?
So how serious is your assumptions?
That's an excellent question, and I prepared a slide for this. Right, so as I said, these assumptions are coming, right, kick in when we prove, when we do this construction of Hecke operators and prove for Rapoph conjectures. So whenever you want to lift these ramification assumptions, then you first have to formulate and prove a certain version of the Rapoph conjecture, which is not easy at this level of structures. All right, again, when you construct these Hecke operators, you need to understand very precisely the geometry and singularities of these integral models. And again, this is not so easy. Okay, but maybe one thing that is something worth doing is when I assume this F is not Q, which I assume that for the simplicity that the Shimura value will be automatically compact. Right, but maybe there's some hope to remove this F not equal to Q by working systematically with the compactification. Okay, but again, there are non-trivial problems arising from that. Right, so in particular, these inputs, that very recent input has to be generalized to the non-compact situation.
Okay, any further questions? If not, let's thank Chao again.